So in this question, we have dropped an object from a height of h, and we've labeled h on the y-axis, and then we draw the object right there. The object falls about halfway down. It's moving with a certain velocity. It's reached a height of 0.5h, and then finally it reaches the ground level, so the height there would be 0. Now we have strategically labeled some times on the right-hand side. When the object is dropped, the time is 0, and when the object hits the ground, we've labeled that time t. But halfway through its fall, we've labeled that time as t prime, and we're going to see why that's advantageous in just a moment. Now, the equation that's going to be most relevant for solving this question is this kinematics equation right here. And what we're going to do is use it twice. So, for example, the first time we use it, we're going to apply it to the motion from when the object is released to when the object hits the ground. So we're going to pay attention to those labels right there. And we can see at those two spots, when it hits the ground, the final height is 0, and the initial height is equal to h. So we're going to plug that data in. So we start out with y, which would be the final height, and that would be 0, minus the initial height, which was h. And then for the initial velocity, because the object was released from rest, we can safely assume the initial velocity is 0. And then when we get to that time interval, take a look at where we've highlighted. We know that the final time is denoted by t, and the initial time was 0. So when it comes to the time interval, which we might call delta t, we take that final time of t and subtract the initial time of 0. So the total time there would just be equal to t. So we'll fill in t for the time. And then we get to the acceleration, and this object is in free fall. So the acceleration is that due to gravity. That would be negative 9.8 meters per second squared. And then again, we get to the time, and we've denoted that as t. And don't forget to square that. We could simplify this equation. The left-hand side becomes negative h. The 0 times t goes to 0. And then 1/2 times negative 9.8 is negative 4.9. And then we have times t squared. So this is one equation, but we're going to have to apply the kinematics formula a second time. So let's set that up. The second time we apply the equation, we're still going to call the initial position right here, but this time the final position is going to be this location right here. So we're going to start plugging in the relevant data. We start out with y, which is the final y coordinate. We can see the final y coordinate from this perspective would be the 0.5h. So we'll plug that in. The initial y coordinate would be h. Still, we're releasing the object from rest, so the initial velocity is 0. And then when we get to the time interval, this time our final time is denoted by t prime, and our initial time is 0. So when it comes to that time interval, which again we can call delta t, we would have the final time of t prime minus the initial time of 0. So that would just equal t prime. So we're going to fill in t prime for the time. And then over here we're going to have plus 1/2 times the negative 9.8, and then times t prime squared. Great, so now we can simplify the equation again. On the left side, 0.5h minus 1h is negative 0.5h. Once again, this term here goes to 0, and then we have this equal to negative 4.9. This will be times t prime, and then don't forget to square it. Might be useful to put that in parentheses like so. So this is the second equation, and we're doing a great job. The other equation we're going to need has to do with the interval of time from when the object falls from here down to here. Notice the question says that it travels half of an h, or 0.5h, in the last 1 second. The last 1 second would be this interval right here. So what that is telling us is that the difference in time during that interval is 1 second. So in other words, we could also say that t minus t prime is equal to 1 second. And this is our third equation right here. This is great. We have to solve this equation ultimately for the time t. And to do that, let's take a look at this equation and this equation. We're going to stack them on top of each other. Now, once we've stacked these equations on top of each other, there's a neat algebraic trick we can perform here. We're going to divide the equations. And what happens is that we have negative 1 divided by negative 0.5. When you do that division, you end up with 2. As far as the h's are concerned, h divided by h equals 1. So you basically just have 2 times 1, which of course is just 2. So the left side just simplifies to 2. Now we have negative 4.9 divided by negative 4.9. That equals positive 1. And then we're also left with this t squared over t prime squared. So this is pretty slick because with this equation, along with the other equation, t minus t prime is equal to 1, we're going to be able to solve for the unknown t. And to do that, let's take a look at this equation right here. And we would wish to get rid of these squares. And the best way to do that is to square root both sides of this equation. So on the left side, you're going to end up with the square root of 2. You can punch that into a calculator. You're going to get about 1.414. And then on the other side, square rooting the squares gets rid of the squares. They cancel each other out. So we just have t all divided by t prime. Great. So let's multiply both sides of this equation by t prime, so that we can cancel it on the right-hand side. And now we can see that 1.414 t prime is equal to t. But it's going to be even better to solve this for t prime. So let's actually now divide both sides by that 1.414. We can cancel that on the left side. So now we have t prime. And then on your calculator, you would just do 1 divided by the 1.414, and you're going to get about 0.707 times t. Now, why did we do that? Because we have that other equation. Don't forget, we have t minus t prime is equal to 1. So what we'll do is a little substitution now. We'll take this value for t prime and we'll plug it in right there. Now, on the left side, we can combine the like terms. We have 1t minus the 0.707t. This gives us about 0.293t. 293t. And then just divide both sides by the 0.293. And when you do that, you will find that t is approximately 3.41 seconds. Remember, that is the answer to part A, because part A wanted the length of time for the entire fall, and that, from our picture, was denoted by just t. So that 3.41 seconds is the correct answer to part A. In part B, we need the height of the fall. We need the value of h. And that's not going to be too bad because we have this equation right here. Let's recopy that and plug in our value for t. There we have it. We do have negatives on both sides of this. If you divide both sides by -1, those negatives would cancel, and then you would just punch in the right-hand side, and you will get a height of approximately 57.1 meters. So this would be the correct answer to part B. Now there was a part C. It said explain the physically unacceptable solution of the quadratic equation in t that you obtained. We actually were able to circumvent the use of the quadratic equation, but there was a point in the problem when we took the square root of 2. You will recall it was back here. When we took the square root of 2, we assumed that the root was positive 1.414. Technically, it would also be negative 1.414. Now, if we had used the negative value of 1.414 and then solved for t, we would have obtained t was approximately 0.6 seconds. Perhaps as an exercise, you can go back and try that. But that's not going to be sensible because t minus t prime was equal to 1. And if we plugged in 0.6 for t and then solved for t prime would be negative. And having a negative value for time just wouldn't make any physical sense in this case. So just a little bit about that part C. But parts A and B, the main parts of the question, were solved. Part A was 3.41 seconds, and part B was 57.1 meters. Thanks for taking the time to watch the video. If you're interested in making a small donation to my cause, I'd greatly appreciate it, but please do not feel obligated to do so. I appreciate you taking the time to watch regardless.